The topic today is naming covalent compounds and the comparison of ionic and covalent compounds. In naming binary covalent compounds, there are 4 rules we must follow. But before we continue, I'd like you to take a picture of the prefixes and the common anions. Take a picture of this because you need it. So in naming covalent compound, you start by naming the first element in the formula. You have a formula. We'll do the example later. You will name the first element in the formula, and then just the way the name is in the periodic table. Then you name the second element. Remember, it's binary. That means it has the first and second element, 2 elements. So you name the first element first, and then the IDE name of the second element. Note there are no ions in these compounds, but whatever the second element is, you write the IDE name, which is this. You get the IDE name from here, common anions. Okay, common anions. You get the IDE name from here. Okay. Remember, covalent bond involves 2 or more nonmetals only. Okay. You name the first element exactly the way it is. The name is in the periodic table. And then you name the IDE name of the second element. Then you come and get the, you look at how many atoms of each element. You use, from here, you get the prefix. If there are 2 atoms, you use 2. If there's 1, something, you use this prefix to indicate the number of atoms of that element present in the compound. There's an exception here. The 4th rule, the exception here is if the first element is only like CO. You name the first element carbon. The second element IDE name is oxide, which is here. Then the prefix, the exception is if the first element is only 1 atom, don't use the prefix on it. You write, then the second element, you can use prefix. So this is carbon monoxide. Okay, so let's do an example. Let's do these examples. These are all covalent compounds. We want to name them. We are given the formula. So we start by naming the first element. Write the name of the first element. The name from the periodic table is nitrogen. You write the name nitrogen. Then you write the IDE name of the second element. Second element is oxygen. The IDE name, which is anion, is oxide. Remember, this is not ionic. There are no ions involved, but you are following the rules. Now, we use the prefix that check the number of, to indicate the number of atoms of each element. So there's 2 nitrogen. So the prefix here is 2. Okay, so di-nitrogen. Then oxygen, the prefix, there's only 1, is mono. So it will be monoxide. So this will be monoxide. Okay? Dinitrogen monoxide. Now, then we do the same thing here. Following the rules, the first element is nitrogen. The second element is IDE name is oxide. Now, we have one nitrogen. So the fourth rule says that if the first element is only one, you don't use mono. So I can put mono in front of here. This second element is one, we can put mono oxide. Okay. And another thing I want you to take note of, this, though I didn't indicate it in the rules, this which is a monoxide, but I remove one O. Okay, we remove one O. That's another rule which I didn't indicate here. So nitrogen monoxide. Then the next one is we have this carbon. We write the first element, carbon. The second one, IDE name of oxygen is oxide. Okay. Then the first element, there's only one carbon, so we can use mono. Then this one, there's two, so dioxide. Okay. This one, the first element is phosphorus. Phosphorus. The second element is chlorine, so the IDE name is chloride. So this is one, so we don't write the mono here according to the rule. Then there's 5 chlorine at chloride. So this will be 5 is pentachloride. Pentachloride. So very, very easy. Very, very easy. In naming covalent compounds is very easy. So let's watch this video that will enhance what we just learned.
That are made of 2 nonmetals. The nonmetals are the elements to the right of the staircase on the periodic table. Now, compounds like these that are made of a nonmetal and another nonmetal, 2 nonmetals, are called covalent or molecular compounds. And that's because the elements that are in them are held together by covalent bonds, and they're held together in groups called molecules. Now, the way we name covalent or molecular compounds is different from how we name ionic compounds. Ionic compounds contain a metal and a nonmetal. The metals are the elements here on the periodic table, and I've written in some of the most common. Some examples of ionic compounds and of how we name them are things like calcium fluoride and iron 2 oxide. So if you have to name a compound, the first thing you want to do is figure out what type of elements are in it. If the compound is made of a metal and a nonmetal, it's an ionic compound. I have a whole bunch of videos on how to name ionic compounds and how to write formulas for them. If you need to name a compound that's made of a nonmetal and another nonmetal, well, that's a covalent or molecular compound, and naming these is what this video is going to focus on. Okay, here's our first chemical formula, N2O3. It's made of 2 nonmetals. We're going to write a name for it following these steps. So here's the first one. It says for the first element, start with the element name. When I'm talking about the first element, I'm talking about the order that these elements are in this chemical formula. So the first element here is nitrogen, N. So it says start with the element name. Okay, so I'm going to put nitrogen down. That's the element name here. Now for the second element, so that's this here, oxygen. For the second element, start with the IDE name. Now the IDE name is the version of the element name that ends in IDE. These are actually the same names that we'd use to name negative ions. So we've got oxygen here. We're going to use its IDE name, which is oxide. Okay? So we got nitrogen and we got oxide. Now, use prefixes to show how many atoms of each type there are. The prefixes, here's a list of them, are like these little tags that we put on the front of each name to tell us how many atoms of each type we have. So N2, we got 2 nitrogens, which means that we want to use this prefix for 2, di. So put that in front of the element name. Dinitrogen. Now O3, which means that we have 3 oxygens. So I'm going to use the prefix tri here and write that in front of oxide. And so the name for this compound is dinitrogen trioxide. We put the element name here, we put the IDE name here, and then we use the prefixes to indicate how many atoms of each type we had. Let's look at a few more examples. P4S10. Okay, for the first element, we'll start with the element name. P is phosphorus. If you didn't know that, you could look it up on the periodic table. For the second element, that's S here, start with the IDE name. So S is sulfur, and its IDE name is sulfide. Okay, so those are the 2 names. Now we're going to use prefixes to show how many atoms of each type we have. We got P4, so that means we have 4 phosphorus atoms. So 4 is tetra. We use the tetra prefix. Tetra. And then for sulfide, we got 10. So we'll use this prefix, deca. Deca. So the name of this compound is tetraphosphorus decasulfide. Let's move on. We're going to add a couple more steps to deal with more complex formulas. Here's the next step that we're going to talk about. Do not use mono on the first element. I'm going to show you what this means by working through naming this formula. We'll start it off just normally. So for the first element, start with the element name. That's carbon. And then the second element, which is fluorine, we use the IDE name, which in this case is fluoride. Okay, now we get to the prefix part, and this is where things change a little bit. So it says do not use mono on the first element. Carbon here, we only have 1 of them. So you might want to use mono and put it in front of here. That would be a perfectly logical thing to do. But for whatever reason, we don't use mono on the first element if there's just 1 of them. We just leave it like this. You don't put anything there. So we have 1 carbon, we're just going to call it carbon. And then for fluorine here, in front of fluoride, I'll put the prefix just like I would any other time. So I have 4 of these fluorines, so I'm going to call it tetrafluoride. So carbon tetrafluoride, not monocarbon tetrafluoride, just carbon tetrafluoride is how we name this, because if you got just 1 of the first element, you don't use anything. PCl5, let's name this. So P, the first element, is phosphorus. Cl, the second element, is chlorine, and chlorine's IDE name is chloride. So there it is. Now we get to the prefixes. Phosphorus here, we only have 1 of them, so we're not going to use mono here. We're just going to keep it as phosphorus. And chlorine, we have 5 of those, so we're going to use penta here as the prefix. So it's going to be pentachloride. And phosphorus pentachloride, not monophosphorus pentachloride, just phosphorus pentachloride is how we name this. Now there's 1 more step that we're going to add. I'm going to talk about that next. Okay, there's 1 more step to keep in mind, and I'm going to show it to you as I work through this example. Okay, Cl2O7. The first element here, Cl, is chlorine, and O here is oxygen. Its IDE name is oxide. Okay, so now the next thing I'm going to do is I'm going to use these prefixes. So I got 2 chlorines, so I'm going to use di for 2 up here. And then oxide, I got 7 of those, so I'm going to use the prefix hepta. Now try saying this compound name. We got dichlorine heptaoxide. Hear that heptaoxide thing? It's kind of awkward to pronounce. So to prevent us coming up with these really weird names, there's 1 more rule. And that's that if you have AO or OO, turn it into O. Here's what that means. We got this heptaoxide here. So to make this easier to pronounce, we turn the AO that we see right there into just an O. So I'm going to get rid of that A, and I'm going to turn this compound name into chlorine heptaoxide. So not heptaoxide, but just heptaoxide. So you get rid of that A if it's next to an O there. Let's do 1 more. P4O6. So the P, phosphorus is our first element, and then O, we got oxide. That is the IDE name for oxygen here. All right, now let's use the prefixes. Switch to our prefix table here. We have 4 phosphorus, so we're going to use the tetra prefix, so tetraphosphorus. And then for oxygen, we have 6 of those, so we're going to use hexa here. And just as before, we end up with this awkward name, hexaoxide. We get an AO, so we're going to get rid of this A here. Shoop. Oh, I always like knock that name out of the way. Hexa oxide, and that turns it into tetraphosphorus hexoxide. You know, I forgot to circle the name in the last one, and this is just so satisfying. So I did it really slowly to make up for the fact I didn't circle the last one. So we get rid of this. We get rid of this A here, tetraphosphorus hexoxide. So I want to do one more example that pulls in examples of all of this. It's like a good review for all of these things. Here's our last formula. This is a really good review. It's just CO. So the first element is carbon. The second element is oxygen. Its IDE name is oxide. Okay, so now for the prefixes. Carbon, we've only got one of them. So remember, don't put anything in front of it. We just call it carbon. But we have one O, and if you have one of the second element, you do use a prefix. So we use the mono prefix here. So mono. Now monoxide gives us this same kind of weird pronunciation thing. It gives us an OO here. So we're going to get rid of this O. I'm going to try to not knock this name out here. Oh, just a little bit. Really good. And we call this, we change the name from monoxide to carbon monoxide, which is probably something that you've heard of before. Here's just some quick information about how we change these prefixes to avoid an awkward pronunciation problem. We only really have this problem with oxide because it begins in O. And so we get rid of the O here in mono and we get monoxide. Then we don't have to worry about di or tri because they don't end in A or O. And then for all of these others, 4 through 10, we get rid of all of these A's. So we get tetroxide, pentoxide, hexoxide, heptoxide, octoxide, nonoxide, and decoxide. So here's how we name covalent or molecular compounds with 2 nonmetals. We just follow each of these steps. One thing to keep in mind, this mono for the first element really confuses a lot of people. So remember not to use mono if there's just one of the first element.
Okay. I would like you to do these practice questions. These are all covalent compounds. Please, I would like you to name them. Pause the video. Pause the video. Okay, check your answers and see if you got these right. Check your answers. Hopefully, you got them right. We want to compare ionic and covalent compounds. We've looked at ionic compounds in the last videos, and we looked at covalent compounds in previous video and this video. We want to compare these 2 types of compound, okay? Let's look at, let's compare this ionic and covalent compound. Okay, this is salt. Salt is NaCl, made up of metal and non-metal. This is ionic compound. We want to see what happens if it conducts electricity. So we put some salt in water. And then, you see that? Salt conducts electricity. You see that? Now, we look at, let's reset. Let's look at sugar. Sugar is a nonmetal. It's a covalent compound. Salt is ionic compound. Sugar is covalent compound. Let's see if it conducts electricity. Yeah, it's not. Even if it is poor, sometimes it's a poor conductor, so it doesn't conduct at all. So it doesn't conduct electricity here. So remember, we are comparing ionic and covalent compounds. Let's look at what happens on a molecular level. On a molecular level, when we put sodium chloride is is metal and non-metal, so you have the positive and negative all interact to form the crystal. So look at, when it hits water, it breaks apart into its sodium ions and chloride ions. You see that? It breaks down into its sodium ions and chloride ions. You see the sodium, the big ones are the chloride ions, the sodium is the small one, okay? Let's see what happens if we put look at this. It's molecule. It's not breaking apart. It's molecules, okay? The atoms are intact. It didn't break apart like the sodium. Okay. We can also look at this in a different way. Sugar looks like this. Look at it. You see? It's intact. It didn't break apart. Okay? So just to show you, compare ionic and covalent. Remember, ionic compounds, in ionic compounds, electrons are transferred. This is ionic compound here, chemical bond. In this case here, ionic compound, electrons are transferred from a cation to anion. You see, there's electron transfer from metal to non-metal, electron transfer. That's the only way it gets stable, forming cation and anion. This is cation, this is anion. Also, sometimes it can be between metal and polyatomic ion, okay? So this is an example showing the transfer of electrons, showing there's opposite charges that attract to form ionic bond. But here is the sharing of electrons. You see the electrons are being shared between hydrogen and oxygen. These are not, there's sharing of electrons involved between non-metals. This is non-metal, this is non-metal, this is non-metal, this is non-metal. And also in ionic, you have metal and non-metal, okay? Like we have sodium is metal, chlorine is non-metal. And then covalent, everything is non-metal. Like oxygen is non-metal, hydrogen is non-metal. Those are some of the differences between them. Also, ionic compounds are mostly solids, while covalent compounds are mostly liquids and gases. Ionic compounds generally have high melting point. Covalent compounds have low melting points. So there are some differences between ionic and covalent. Let's also look at compare the properties of ionic and covalent compounds. Properties of ionic and covalent compounds. Let's watch this video.
Welcome to our lesson on the properties of ionic and covalent compounds. As you might have guessed, in this lesson we're going to be comparing and contrasting some of the general physical properties of both ionic compounds and covalent compounds. So let's look at some of those properties. We'll have ionic on this side, and we'll compare them to covalent properties on this side. Many of these properties we're going to be looking at are basically guidelines. Again, there's always going to be exceptions when some compounds don't have particular properties. They don't have to have all of the properties, but this is a general idea of the properties ionic compounds have versus the properties covalent compounds have. So let's start with ionic compounds. As we saw in a previous video, ionic compounds form crystals. That's pretty much a guarantee. They're always going to form crystals because of the nature of the way positive and negative charges line up. Related to that idea of all those positive and negative charges creating a very strong structure, they have very high melting points and high boiling points. What does that mean? Well, it means that they're pretty much always going to be a solid, because it takes a very high temperature for them to melt and an even higher one for them to boil. Their strong structure also makes them very hard, but at the same time brittle. They're going to shatter very easily if enough force is applied. They can't be bent or deformed, but they can shatter. Ionic compounds are usually soluble, meaning they can dissolve, in water. And the last one, that's a really big giveaway for ionic compounds, is that when ionic compounds are dissolved, or if they're molten, meaning they were melted, they're in a liquid state, they conduct electricity. Now, anything that conducts electricity when it's dissolved is called an electrolyte. So ionic compounds are electrolytes. When they are put in water, the ions separate from each other and they become free-moving ions, which allows electricity to be conducted in the liquid. So ionic compounds are electrolytes, substances that dissolve in water and then conduct electricity. They do not conduct electricity when they are in the crystal solid form. These are the key properties of ionic compounds that are frequently used to identify them. A lot of the covalent properties are going to look like mirrors of the ionic ones in terms of just being opposites. So whereas ionic is almost always a solid crystal, covalent can be solid, liquid, or gas. They have relatively lower melting points and boiling points than ionic compounds. They're also not good conductors. They're poor conductors. They either don't conduct electricity or heat at all, or it's just not a very good job of it. Poor conductors. They typically don't dissolve in water, don't usually dissolve in water, which also means that they're not electrolytes. And the last one is that they are very frequently flammable. Okay, that's a big giveaway for covalent compounds. Ionic compounds are really never flammable, but covalent compounds are often flammable. That wraps up our comparison of properties for ionic and covalent compounds. Any questions?
I would like you to look at these, answer these practice questions, fill in the gaps. That's here. You look at this, is this solid or liquid? You write it down. Is melting point high or low? You just say either high melting point or low melting point. You don't have to say the exact melting point. Electricity in water, is it either it conducts yes or no? Okay. Then type of bond, is it ionic or covalent? So you are applying what you've learned so far in answering these questions. Okay, pause the video. So you see high or low, yes or no, ionic or covalent, solid or liquid, or gas. I should include gas here, solid or liquid or gas. Okay. So here we go. Did you get it right? That's it. I hope it makes sense to you. Thanks for watching.